Hi, my name is Parker Chalk. Under the advisement of Dr. Yu Kao, I have studied high power silicon carbide inverter design over the summer. So, when powering an electric vehicle, our energy is stored in a battery pack, and the energy output is an AC motor. And the inverter's job is to convert the energy in a battery pack to the energy output for an AC motor. It's a bridge between the two. And so it works to convert direct current into alternating current. In this context, I'm studying a three-phase inverter. This inverter produces three phases of alternating current that can be seen on the right. It does this by switching on and off six different switches very quickly with the help of the filtering of the motor to generate a sinusoidal waveform. These six switches are implemented with the MOSFETs mentioned earlier. So this is the objective of my research. What's new? And a new technology emerging within the last few years is silicon carbide MOSFETs. They have some new advantages as well as some new design challenges. And this leaves us with some new inverter control ideas that can be tested. So, some related work to my research. There's been study on temperature and efficiency of silicon carbide devices. This figure on the left gives us information on the on resistance of the MOSFET. This part's important because the more resistance a MOSFET or switch has, the more loss there will be. And so to increase efficiency, we want as low loss as possible. The figure on our right shows a little bit more about some mismatches. These are all different devices, and they all act a little bit differently under test conditions. And this will become important later with the proposed implementation that I've been studying. So, some other related work in this is inverter topology. So far, we've only been looking at voltage source inverters, but there's also a current source inverter that has also been investigated. This involves a current source other than a voltage source for powering the inverter. It's an interesting design choice, but I ultimately decided to pursue the voltage source inverter more because of the application I'm working with. An inverter for an electric vehicle requires the use of regenerative braking when the inverter kind of acts in reverse, where energy comes from the motor and goes back into the battery pack. And this is possible, though quite a bit more difficult to do with the current source inverter. So for that reason, we decided to stick with the voltage source inverter. Some other related work in this was parallel switching designs. This involves putting multiple MOSFETs or switches in parallel with each other to produce higher efficiency inverters. This can be seen on the figure on the left, where using more inverters, in this case in parallel, produces a lower temperature. So some of my preliminary key research takeaways. Silicon carbide MOSFETs are going to be used. They have superior material characteristics. The current source inverters most likely won't be used, or at least not for the moment, because of regenerative braking. And parallel switching is going to be focused on in this research. It's closely related to my application priorities, and it offers some new switching strategies and some interesting design trade-offs to consider. Ultimately, this preliminary key research is going to narrow my research topic. So, going into parallel switching a little bit more, parallel MOSFETs offer opportunities for flexible inverter operation. So there's some key takeaways between using a parallel MOSFET structure and a single MOSFET structure. The first is power density. Using more devices is going to make the overall inverter less dense overall. Another thing to consider is efficiency. 2 slides ago, I showed that figure that displayed that having more MOSFETs in parallel, it can increase the efficiency of an inverter. Similar to power density, having more devices is going to cost more as well. So this is another thing to consider. The fourth point is something that I'm going to take particular note in is flexibility and load response. Having multiple switches can allow some interesting control ideas. For example, interleaving them, not using them all at once. The last point is reliability and fault tolerance. Having multiple MOSFETs in parallel, all that can be controlled individually, can have some really nice fault tolerant applications. Say a semi truck is using this inverter and one of the switches breaks. Normally, if it was a single MOSFET, the truck would be completely out and would need a replacement inverter. But if it has parallel MOSFETs in its inverter, if one breaks, it can still function at, say, half current capacity. And this fault tolerant is going to be very important for the application of trucks where breaking down is very, very costly. So my key contributions in this research is high current application. Again, I'm looking at inverters for the use in semi trucks, which requires much higher current than a passenger vehicle. So there's a lot less academic research into parallel MOSFET inverters for high current electric vehicle applications. Another part of my key contributions is switching modes. So the more a switch is used, the less time it will last. And also, the longer a switch is on, the more power is lost. And so a key idea is to have the switches alternate in low current demand. So in high current applications, when the truck needs a lot of torque, switches A and B are going to turn on and off together, kind of acting like one big switch. But in low current applications, say in going a constant speed on a highway, they are going to interleave where A will be on and B will be off, and then they'll switch. My research will look in to see how this affects efficiency and also what kind of trade off we can expect between the efficiency of doing it this way and some lifetime benefit to the device itself. So, in my approach and methods, I first built a model of this on a program called Simulink. This figure here shows the implementation of a three-phase parallel MOSFET inverter using 12 total MOSFETs. The goal of this modeling was to get a control scheme to get the paralleled MOSFETs to behave as one switch, but also as interleaved switches for some efficiency testing. Once that was done, I moved on to Plex, where I implemented that switching strategy. Some important notes about the switching strategy is that an upper switch cannot be closed while a lower switch is closed. This creates a short circuit, which can destroy the inverter. Ideally, also, the upper left MOSFET and the upper right MOSFET are on an equal amount of time. Same is true with the lower left and lower right MOSFETs. I want these to be equally used to try to share a lifetime benefit of the overall inverter. This was done in Plex, and up to this point, analysis of all has been qualitative. Plex offers a more quantitative analysis. This lets me do efficiency calculations and utilizes some non-idealities in MOSFETs. This is like the on resistance of the MOSFETs in one of the first figures. More realistic feedback control is another thing Plex has to offer. I have an actual motor model that I can use to see its response to my inverter. Efficiency maps are another really important part of my research. They visually depict the inverter efficiency at every speed and torque motor combination. On the y-axis, we have torque in Newton meters, and on the x-axis, we have speed in RPM. The color gradient indicates the overall inverter efficiency. So here are my results. The synchronized MOSFET switching is more efficient than interleaved MOSFET switching at every torque and speed combination. To reiterate, the synchronized MOSFET switching is when both switches are turning on and off at the same time synchronized. And the interleaved MOSFET switching is when they are alternating. So to summarize, Interleaved switching is less efficient than synchronized switching, but still offers a potential lifetime benefit. This ties into some future work where lifetime analysis of interleave switching versus synchronized switching can be studied to see what can be expected, trading efficiency for life expectancy. And drive cycle data can be used to determine these expected gains in lifetime. To summarize my work here, I showed that using a synchronized MOSFET switching scheme is more efficient than an interleaved switching scheme with the efficiency maps generated from Plex. This will be used to develop future work where I will look at the interleaved switching efficiency and see if that less efficiency is worth a trade off in extra life expectancy for the inverter using expected gains in lifetime. Thank you for listening to my presentation.